So in this video, I'll be describing how you can use Microsoft Excel to calculate three very important pharmacokinetic parameters of a drug. First, the initial plasma concentration. That is that hypothetical concentration of the drug at the instant at which it was administered. So of course you cannot technically measure that using any analytical technique. You can at best extrapolate from your data to get this value. But because it's important, I will describe this. Second, I'll describe how you calculate the elimination rate constant, which describes how fast your drug would be eliminated from the central compartment, from the plasma. And third is the area under the curve, which describes your exposure to a drug that is administered. And we could do that in two ways. I'll talk about that. So first here, let's look at the first way by which you could calculate AUC and the way by which you predominantly calculate the elimination rate constant and the KE and the CP0. So let's assume our data, our drug concentration time data follows simple first order kinetics. That is, there is a constant elimination rate value, elimination rate constant. It does not change. So that is, this drug is eliminated at this constant rate. And in order to, so let's look at this data set where you have time and concentration in plasma values. So at 2 hours, you detected 90 nanogram per liter, and at 24 hours, it's come down to 30 nanogram per liter. So how do you calculate these important parameters? So let's first of all assume constant elimination rate, and you'd have to, if you plotted plasma concentration versus time, you'd get that nice hockey stick type curve, which again confirms that it follows first order kinetics. And like I've said before, it's hard to work with this type of data, using graphing methods. So it's easier to have a straight line graph. And in order to do that, you basically have to first convert the plasma concentrations into natural log of the plasma concentration. And you do that in Excel using the ln function. So just hit equal to ln, which stands for natural log, and in parentheses the value you want to determine the natural log of. And next you do a scatter plot of the natural log of the plasma concentration versus time on the x-axis. And so here I've calculated the natural log concentrations nicely, it's over here. And the next thing is I then plot the second type of transformed data. That's the data on the right. It fits nicely into y is equal to mx plus c, where m is the slope, and of course that means your slope is equal to the negative value of the KL. And your CP0, your CP0, initial plasma concentration, is your intercept on the y-axis. So you can, because it's a straight line, you can basically interpolate into to the y-axis, and that gives you your CP0. So for the data set I just gave you, my y is equal to, my relationship is y is equal to minus 0.05x. X is time, of course. That means KEL is equal to 0.05, not negative 0.05, but it's 0.05, and natural log of the plasma concentration at time 0 is 4.6. And in order to get what that value is, all you need to use is the exponent function. And if you do that in Excel, that is equal to EXP, and in parentheses, that number, 4.6045, it will return the actual initial plasma concentration, that is your CP0. And of course, now we have the slope. If you like, you can also calculate the half-life. Half-life is equal to 0.69 over KEL. We know that half-life is the time it takes for a drug's concentration to reduce by 50%. And finally, if this relationship is true, that is, if it's a simple first order kinetic elimination, AUC actually is going to be equal to CP0 over KEL. Very nice and smooth. So based on this simple assumption of first order kinetics, you could basically get all 4 parameters. And so, but the problem is, most drugs do not follow first order kinetics because some drugs are sequestered in fat tissue, at the same time sequestered in muscle tissue, and so the rate at which the drug exits from this compartment is really variable. And so let's look at this data set, which does not necessarily follow first order kinetics. So I've tried to plot the data in the graph on the right, and I don't know if you see this already. So I did say that you really can't calculate, you really can't measure, that is, using an analytical technique, measure the amount of drug that is in the blood, in the plasma at time 0, the instant at which you administer the drug. So you have to always interpolate to get that value. If we could assume first order kinetics, we could use the straight line graph and interpolate to the y-axis and get that value. But because this data set does not follow simple first order kinetics, there has to be another way to get that. The other thing with this kind of data is because you can assume just one simple elimination rate constant from the start to the finish, that is, your elimination rate constant varies with time. The last part of the curve really depends on what time you measure it and also the sensitivity of your technique. And so, because really AUC is the area under the curve from time 0 to time infinity, you have to be able to estimate time 0 to time infinity in some way for the last tail, the last tail of the curve, that is from point G to infinity. You can't assume a constant elimination rate constant for this point, and so you have to be able to estimate 2 things. One is your CP0, and second is your AUC for the tail of your curve, that is from time point G to infinity. So what do we do? So first off, using the trapezoid rule, you can use that nicely to calculate accurately the AUC of the different time intervals. So for example, between B and C, so the concentration at B is 123, the concentration at C is 101. If you take the average of these 2 values, that is 123 plus 101 divided by 2, and multiply that by the time interval. The time interval here is 1 to 0.5. You would get the AUC for that segment, and you can do that for the following segments, C, D, and so on and so forth. So you would get a value like this for the region between B and C. But the problem is, how do you estimate from time 0 to time B? So if you arbitrarily, just made a guess, some person might make a guess like this, another person might make a guess like this, another person might make a guess like this, which are 3 different AUC values that you're going to obtain for this initial trapezoid. And so you have to be able to estimate what your CP0 is. And to do that, we're just going to use an assumption of simple first order kinetics for the earliest time point in your figure, that is time points B and C, and you do a plot of your plasma, of your time versus log of the plasma concentrations like we had done before, and you can get an intercept and use that intercept to get your CP0, and with that you can calculate AUC for time points A to B. So that's nice. And for the last point of a figure, you would do something similar. That is, you're going to assume that the elimination rate constant of your last 2 points, that is 8 hours and 16 hours, that the elimination rate constant there, you're going to assume that for the last tail of this curve. And so with those 2 time points and the natural log transformed values of this plasma concentrations, you can also calculate an elimination rate constant for that region. And your AUC for that last region, that is from G to infinity, is equal to the last plasma concentration measured, that is 0.3 in this case, that is the CP last, and divided by the KEL of that last segment, last measured segment, which you determine graphically. And that would give you your AUC for the period between G and infinity. And now you could sum up all the AUCs, and with that you can get the AUC for for this data set using the initial using both methods, that is using the trapezoid rule, as well as I would like you to measure the AUC assuming first order kinetics for this data set, what it would be using extrapolated CP0 values based on an assumption of constant elimination throughout the disposition of the drug. All right, that's it, and I would like you to enter this data on the appropriate site, appropriate question in Sakai. All right, thank you, and have a good day.